The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
The inductive attenuator demonstrates the Laplacian nature of magnetic fields in free space, the way that currents distribute themselves on the surfaces of perfect conductors, and the use of the vector potential in describing magnetic fields in two-dimensional systems. Provided that the magnetic flux density is in the xy plane and depends only on x and y, it can be represented by one component of the vector potential, A sub z. In free space, the vector potential satisfies Laplace's equation. Separable solutions to Laplace's equation that are periodic in one direction decay in a perpendicular direction. Here, the direction of periodicity is x, while the hyperbolic sign is a combination of exponentials representing the decay in the y direction. In this model, the floor is the xy plane. The altitude of the surface is the vector potential. Here's the direction of periodicity. Here's the direction of decay. Because it represents a solution to Laplace's equation, every point on the surface having a positive curvature in the y direction must have a negative curvature in the x direction. This is why periodicity in one direction implies decay in the other. For this solution to Laplace's equation, three of the rectangular boundaries have a constant vector potential. The fourth is a sinusoid. In our physical situation, this fourth boundary is elevated to a uniform vector potential. This can be represented by a superposition of these solutions. To represent a uniform vector potential, solutions are added that have a shorter wavelength. By the nature of Laplace's equation, these have a more rapid decay than the fundamental in the perpendicular y direction. Here are the magnetic flux lines represented by the vector potential. These are the boundaries where the vector potential is 0. This is the boundary that is elevated in its vector potential. A surface of constant vector potential is one that sustains no normal component of the magnetic flux density. It can be the surface of a perfect conductor. Here, these boundaries of 0 vector potential are perfect conductors, carrying that surface current necessary to terminate the tangential magnetic field. This boundary of elevated vector potential is also a perfect conductor. The difference between the vector potential on this electrode and on the wall is the net magnetic flux per unit length passing inward through the gap. Similarly, the difference between the electrode vector potential and the wall potential here is the net magnetic flux per unit length passing outward. The surface current passing outward on the electrode is returned in the side walls and bottom wall. In our model, lines of constant altitude are lines of constant vector potential. In two dimensions, lines of constant A sub z are lines of magnetic flux density. So the wires are the lines of magnetic flux density. If you're familiar with using a scalar potential to represent an irrotational electric field, the role played by the scalar potential is being played here by the vector potential. Lambda is the flux per unit length passing through the gaps at the ends of the top electrode. In the electroquasi-static analog, this flux is analogous to the voltage between the upper electrode and the wall. The analogy is intriguing. It is the potentials that are analogous. In the electroquasi-static situation, the field lines are perpendicular to the lines of constant scalar potential. Here, in our magnetoquasi-static situation, the lines of constant vector potential are the field lines. Although we may think of the fields as two-dimensional, their physical embodiment is actually three-dimensional. Here's the driving electrode. Here are the sidewalls. The current outward through the driven electrode is either returned in the sidewalls through connecting wires or is induced in the bottom wall. The current outward through the driven electrode is either returned in the sidewalls through connecting wires or is induced in the bottom wall. Over any cross-section, the fields are two-dimensional. The closer the bottom electrode is to the driving electrode, the more the current circulating through the bottom electrode. The current from this 20 kilohertz source passes forward through the upper electrode and is returned in the sidewalls through these shorts. So that we can measure that part of the current circulating through the bottom electrode, it's insulated from the sidewalls, but shorted to them at each end. Through this conductor, current induced in the lower plate can therefore return in the sidewalls. To complete the loop, the lower plate is also shorted to the sidewalls at the far end. Presumably, these shorts have a sufficiently low impedance that the lower plate remains at essentially zero vector potential. That is, the shorts are good enough that little magnetic flux leaks through the gaps between the bottom plate and the sidewalls. We'll measure the current induced in the lower plate with this current probe. How much total current is induced in the bottom electrode for a given voltage applied to the upper one? This is the actual apparatus. Here are the sidewalls, insulated from each other. Here's the top plate. Current from this source passes forward through the upper plate and is returned by the shorts through the sidewalls. Here are the connections at the back end. The source is connected by the center conductor of a coaxial cable to the upper electrode, here. The driving current is returned to the source by these wires and the coax shield conductor. These leads are connected to the top trace of our scope. The top trace is the driving voltage. Here at the back, the bottom plate is shorted to the sidewalls. It is also shorted at the front through these wires. We measure the current induced in this electrode by means of this current probe. The lower trace on the scope represents the output current from the probe. It represents the net current induced in the lower electrode. Here's how the current induced in the lower electrode varies as the driving electrode is lowered. As the spacing is increased, again with the driving voltage essentially held fixed, the induced current decreases. As the driving electrode approaches the lower electrode, it increases again. With the electrodes this close, almost all of the current in the upper electrode is imaged in the lower electrode. The current in the lower electrode is the integral of the tangential magnetic field intensity over its length. By the nature of Laplace's equation, this field intensity becomes weaker as the distance between top and bottom electrodes increases. As the distance between electrodes increases, the fraction of the current that returns in the lower electrode is reduced. The walls have a width W and are separated by A. We've been adjusting the distance B between the excitation and detection plates. Our modal theory tells us that this output current, I sub 0, has this dependence on the AC excitation voltage amplitude V. Here's the dependence on the distance between excitation and detection plates. The normalizing current, I, is proportional to the driving voltage, V, and inversely proportional to the angular frequency, omega. To make a quantitative comparison between what we predict and what we measure, we need to compute the normalizing current, I. The measured applied voltage, V, is 8.2 millivolts peak. The width, W, is half a meter, and the frequency is 20 kilohertz. So in this case, I is 0.53 amperes. With B equal to A, the measured current I sub 0 is 2.6 milliamps peak. So the natural log of this current, normalized to I, is minus 5.3. Graphically, this is the predicted dependence of output current on the distance between upper and lower plates. The vertical axis is the natural log of the current in the lower electrode normalized to the current I, which we just computed. The horizontal axis is the distance between lower and upper electrodes, normalized to the distance between the sidewalls. The data point which we've just taken was for the electrode spacing equal to the distance between the sidewalls. So our data point goes here. Here are some other values which we've measured. The current I sub 0 in the lower electrode does have the correct variation with spacing between the electrodes. However, it's displaced downward from the predicted curve by essentially a constant factor of 8 or 9. The main reason for this discrepancy is the flux linked by the wires used to provide the return current paths. The rate of change of this flux makes an addition to the measured terminal voltage that makes the normalization current I larger than it should be. To see this, we can use a loop of wire rather than the terminal voltage to measure the flux through the gap between the upper electrode and the left wall. The loop passes along the outer edge of the upper electrode and is returned just outside the adjacent conducting wall. So arranged, it links little extraneous flux at the ends. Also, because it will be connected to the high impedance of the scope, it carries a negligible current, and so the integral of the electric field intensity around the loop, which is the voltage at the terminals, does not have a part due to the resistance of the loop. The top trace is the electrode driving voltage. Here's the terminal voltage of the loop. With the spacing between electrodes equal to that between the walls, the terminal voltage of the flux loop is about 1.2 millivolts peak. Under these same conditions, the upper electrode terminal voltage was 8.2 millivolts peak, about a factor of 7 larger. This data point and others we've taken using the flux loop rather than the upper electrode terminal voltage not only have the predicted dependence on electrode spacing, but more nearly the predicted absolute magnitude as well. The inductive attenuator has illustrated the Laplacian nature of free space magneto-quasi-static fields. The magnetic field induced by applying a voltage to the upper electrode decays, essentially exponentially, into the rectangular region, bounded by the essentially perfectly conducting sidewalls and the bottom electrode.